are some issues which we will now discuss. Consider the inductor current. I will draw the time versus inductor current, and I will keep the markings in such a way that the duty cycle is less than 0.5. I want to show few cycles. Now let us say this is one cycle, second cycle, third cycle, fourth cycle. Now these are the duty cycle gaps. So in the first cycle, duty cycle less than 0.5, second cycle, same duty cycle less than 0.5, third cycle like that. So let me mark the upper tip and the bottom tip of the inductor ripple. So let me mark it like that, and the inductor current will stay within this ripple. So during the time of this duty cycle dt, inductor current is going to rise like this, and during the time of the 1 minus dt it is going to fall. Rise, fall, rise, fall, rise, fall, so on. Now this would be the normal expected steady state value of the inductor current. Now let us see what happens if there is a disturbance. Now I will introduce a disturbance here. I'll just offset it. Disturbance could have occurred due to any number of reasons. Let's say if this disturbance occurs, the inductor current will start on from here. It's an integrator. It will start on from here with the same slope, V in minus VB divided by L. So it will go parallel to this line. So let me draw it parallel to that line, and then after it hits this top limit, it will go parallel to the downslope of minus VB by L, then upslope, downslope, so on. You see that it progresses in this fashion. And what is the takeaway from this is that whatever there is a disturbance, the disturbance finally decays to 0, and then the disturbance is removed, and the normal inductance steady state value current flows. Now take the example of another case, T versus IL. Now I am going to increase the duty cycle to beyond 0.5. Same time period, duty cycle is higher. Same time period, duty cycle is higher, and so on. So now when the duty cycle is greater than 0.5, what happens? Let me again mark the top and bottom of the inductor ripple. I will keep it same. And what is the steady state normal expected value of the inductor current? Let me first draw that. So this will be V in minus VB by L. This will be minus VB by L, negative slope, positive slope, negative slope, positive slope, negative slope, so on. So this is the normal expected steady state value of the inductor current under duty cycle greater than 0.5 also. Now here also, like here, we will introduce a disturbance. A disturbance has occurred due to whatever the reason. So when you introduce a disturbance, now from this point onwards, it will start going parallel to this line. It will have the same inductor slope. So let us say it takes this line, it hits the top value here, that is the IL reference value, then goes down, resets again, because this is the time duration when the Q of the flip-flop is low, hits the the end of TS, when the clock again gives a small pulse and sets the flip-flop, again it will rise, then goes down, continues going down, here it will get reset, so on. And you see that the disturbance starts growing. Cycle by cycle it starts growing, it becomes unstable. So it never converges to the expected steady state value of the inductor current. So when the duty cycle is greater than 0.5, the inductor current will start diverging and it will not be stable when you do current controlled operation in this fashion, where this is the IL reference. The top of the inductor current ripple is the IL reference. How do we solve this problem? Let us seek a solution and try to find out how to do that and implement that. Let me consider the problem case waveform. Here the duty cycle is greater than 0.5, and we see that if we give a disturbance, the disturbance keeps growing and leads to an unstable inductor current waveform. Now this line here, this top line here, where the inductor current is comparing with that line, is the IL reference line. So let me highlight that with a different color and let me indicate that. So that is IL ref. So whenever the inductor current reaches IL ref and tries to cross that, then the error changes direction, becomes negative, and then resets the flip-flop. But that is not happening in a proper way when the duty cycle is greater than 0.5. Now let us try to change the shape of this IL reference line. Instead of being a straight flat line, let us introduce some slope. So what I will do is try to extend this axis, and then let me draw a line which is having the same slope as the falling slope of the inductor. Now the falling slope of the inductor here is minus V0 by L or minus VB by L for the case of the buck converter. So we will try to use that same slope, continue it upwards. Now this is the slope line that we will use for this time period Ts. We will repeat the same slope line for every time period. So using that as a marker, let me repeat the same slope line for the next time period, then the next time period too, and so on. Now this sawtooth type of waveform will become the new IL ref. So when you use IL ref of this nature, you see something nice happening. Now let us take the same disturbance and let me allow the inductor current to go parallel to what is supposed to be the steady state value. So it goes parallel. Now hits the boundary here. It hits the IL reference here, and at this point it tries to cross over, and the comparator goes, the error goes negative. The comparator output will see to it that the reset of the SR latch resets, is asserted and resets the Q value. So thereby it will then start having a downslope, and the downslope is going to be along the same parallel, because the falling slope for the inductor current is minus V0 by L or minus VB by L in this case. So you see that in just one switching cycle, the error has been reduced. So the error is from there on continues to follow the steady state value. So you see that any error quickly converges and the error is removed within a switching cycle. This is the beauty of having this type of a sloped sawtooth shaped IL ref. So you should give the slope here for the IL ref same as the falling slope of the inductor current. Then you are safe and the error will be removed within a cycle. So how to give a slope? Now this was the old IL ref. To this old IL ref, you have to compensate and see that you have this kind of a slope. So this is called slope compensation. So current control with slope compensation will give you the best results, where even if there are errors, the errors will be removed within a cycle and the system will be stable. So this can also be proved mathematically, what I have just shown by graphs. You can refer to literature on DC-DC converters or any of the NPTEL courses on DC-DC converters. We shall now see how we can generate an IL reference which is of this form. It should be in this kind of a sawtooth form, and the slope being same as the falling slope of the inductor current. And once we generate that, then our current controlled converter is ready for performing battery charging operation with MPPT. Let us now try to understand what slope compensation is and how to obtain the slope compensated reference waveform. Let us understand it with the help of some waveforms with respect to time. I will plot IL ref, which is nothing but a constant DC value. So the inductor current waveform is compared with this constant DC, and then that is how the current controlled output is generated. But this has a problem for greater than 50% duty cycle, where it will become unstable. So therefore we need to generate a slope compensated waveform. Let me now draw this type of wave shape, and this slope should be VB by L, should have a magnitude of VB by L. So this will have a magnitude of VB by L, and this is called I slope, let's say. And the new reference will be IL ref minus I slope, and that will look like this. So this will be the new current reference that we need to use for doing the current control. So the inductor current should get compared with this slope compensated current reference. So this will be the slope compensated reference that we will use. Now how do we get this wave shape where the slope is same as VB by L, that is the downslope of the inductor current waveform? So the question, how to generate this waveform? So if we look at the inductor current, the inductor current here, what we have drawn, during 1 minus dTs period, during the time when the switch is off, the slope of the inductor current is minus V0 by L or minus VB by L. And the magnitude of that slope is VB by L. So this inductor, by the Faraday equation, the VL, voltage across the inductor, is given by L DIL by dt. Let us write that down. VL is equal to L DIL by dt, and during the 1 minus dTs period, IL is minus VB by L integral dt. And I slope, because here you are talking of a positive slope, if I remove the negative sign, considering only the magnitude of the slope, will be VB by L integral dt. So how do we obtain this current wave shape? How do we get this wave shape by implementation? So what we can have is, we can have a controlled current source like this, and that controlled current source is connected to a capacitor like this, and let us say Cs is the capacitance, and then you can monitor the voltage VCS across here. And then let us say there is a current I that you have decided for the current source. So what is the voltage across the capacitance? So the voltage of the capacitance is 1 by Cs integral of I dt, which is I by Cs because I is a constant, integral of dt. Now observe this and this, the coefficients of integral dt, Vb by L and I by Cs. Now comparing these two, we can write I as Vb by L into Cs. Now let us make I here Vb by L into Cs divided by Cs into dt would be the voltage across this capacitance. So the voltage across this capacitance will follow in this wave shape. It's a voltage equivalent value of I slope will follow this wave shape with this exact slope Vb by L, because Cs will cancel. Now this is an integrator, and as long as the current here is constant, this will keep on integrating. It will not come down to zero. So there has to be a reset mechanism. So let us connect across this a switch. So the current source, I will set it at Vb Cs by L. Now I will connect a switch there across the capacitance and drive that switch on or off from the clock. So whenever there is a clock, so that will switch this on, it will discharge this capacitance, bring it to zero. So during that period of clock duty cycle, this will come down to zero. Then again it starts integrating, and then at this point clock will come into the picture. This will come down to zero. The clock waveform looks like this. We have seen this earlier. It is a set of narrow pulses occurring at every TS period. At the beginning of every TS period, this is a very, very narrow duty cycle pulse, and it is during this very narrow duty cycle, it will turn on this switch, short circuit the capacitance discharge through this one. You can put a resistance in series, a small resistance in series, to probably limit the current. Now this, if you place it along with these set of waveforms, it will look in this fashion. So let me draw. So these are the positions when the clock will appear. So you will see the clock signal. So a very narrow duty cycle pulse occurring at the start of every TS period. It will reset the capacitance and then bring it to zero. Then the capacitor will keep integrating, it will build up, and at the occurrence of the next clock, it will reset to zero. Again it will start integrating, and the occurrence of the next clock, starting of the TS period, it will reset to zero. So this will keep happening. So in this way we can generate this I slope waveform and use it for obtaining the slope compensated reference. Now let us take our current controlled converter charger circuit. Earlier we had IL ref directly here. IL ref here was a constant DC value. So we will replace it with the slope compensated reference. So what we will do is that we will remove IL there, and I will say that this point we are going to give a slope compensated reference. Now how do we generate that? Let us have IL ref here shifted back a bit, and I will compare it with this I slope. So let me have a controlled current source. This controlled current source will have a current value I, which is dependent on the sensed value of Vb divided by L into Cs. So put a capacitance there, and across the capacitance I will put a switch, and this switch I will turn on based on this clock signal. So whenever the clock gives a high, this will also turn this on, reset this capacitor, and then when this goes off, this will start integrating. This resistance is put here just to limit the current, and it will also put in a time constant, CS into R time constant into picture, but it will be a small time constant which will reach 5 times time constant by the time the clock duty cycle pulse finishes. So this value what you would be giving there is I slope, and you subtract it from IL reference and give this as the compensated slope compensated reference. Now if you look at this wave shape is just the DC. And what about this wave shape? So let us first set the current reference here. The current value is VB into CS by L. Observe that VB is the sensed value. So the current reference here will change according to the output voltage here. And if you do that, then here you will get a positive slope sawtooth waveform like this. IL reference minus this will give you a sawtooth waveform like this, and this will form the slope compensated reference that you will provide to this controller. So now IL, whenever it is greater than this slope compensated value, then the error here will go negative and this will go positive and reset the flip SR latch. So this is how the slope compensated current controlled converter will work and charge the battery. Now this IL ref here, if it is coming from the output of the MPPT charger, that is you are sensing the voltage and the current from here and passes through the hill detection or hill climbing algorithm, output of that you give it here, then the current reference here will keep changing according to whatever peak power the PV panel can deliver. And then as this reference changes, you will see that the current here will increase or decrease depending upon the insulation value. So then that becomes a MPPT based slope compensated current controller battery charger for a PV source. Including the MPPT block, we can include the MPPT algorithm block here, like similar to the hill climbing algorithm. It needs two input. One input is VT, the terminal voltage of the PV panel. The other input is IPV, the current flowing through the panel. And the output of the MPPT, we will give it to IL reference here. So this value will change as we saw earlier in this fashion, and IL ref will keep changing depending upon insolation, and it will try to draw set the IL reference here such that maximum power can be drawn from the PV panel. So as this IL reference gets set, and the slope compensated current control converter will make IL value same as this IL reference, and thereby charge up the battery and the load together at the best power available from the PV source.